In this tutorial, I'm going to be looking at shaping a light beam or multiple light beams along the spatial and/or temporal axes. So let's say we've got a beam like this coming from our light source. The example we're looking at here is a beam that's spatially Gaussian in the XY transverse direction, and in this case it's a short little pulse along the time axis. And then perhaps we pass it through some optical system to reshape it spatially in the XY directions, shaping the beam in the transverse direction. Now it's spatially a Hermite-Gaussian beam in this case. We've taken that input source and then we've mapped it onto our output beam, which is defined in the X and the Y directions. Or perhaps we want to shape the beam along the time axis. So we take that short pulse from our source and then we shape it along the time axis, the longitudinal direction, the propagation direction. And now in this case, we've got a long rectangular pulse in time. We can take our input source and then we can map it onto our desired output beam as a function of time. Or more recently, it's also become possible to shape arbitrarily along both the spatial and temporal axes at the same time. That is, we take our little spatiotemporal focus from the source, a small spatial spot as a short pulse, and then we shape it into some arbitrary volumetric light blob in all three dimensions at the same time. Now in this output beam, we can have any arbitrary amplitude, phase, polarization at any spatial position at any delay. So we can define the output beam as a function of x, y, and time. There'll be an emphasis here on the use case of taking a beam, shaping it spatially along the transverse axis, and/or shaping it temporally along the longitudinal axis, and propagating it through a multimode optical fiber. But that's just one of the many possible use cases. The principles we'll be looking at apply regardless of what you're looking to use your beam for. I'll be looking at a few of the most common spatial and temporal beam shaping scenarios. So first, spatial beam shaping using a single phase mask, the simplest scenario, and the one that's also probably used the most experimentally. You just want to take the beam coming from your source, spatially Gaussian beam in this case, and convert it into some other type of beam, in this case a HG11 mode, also known as an LP21 mode. It's a one in, one out system. One beam comes in, one beam comes out, and just one phase mask, no time manipulation, purely spatial manipulation. This one mask approach is experimentally simple at the expense of loss. Second scenario, spatial beam shaping of a single beam using two or more phase masks. So this is still a one beam in, one beam out system, but with some advantages in terms of things like efficiencies. More than one mask will let you transform one spatial field into another with 100% efficiency or close to it. Third scenario, spatial beam shaping of multiple beams simultaneously using multiple phase masks, typically called a multiplane light conversion system, MPLC. In this case, multiple beams come in, often from independent mutually incoherent sources, and then each gets mapped onto its own orthogonal output beam. So this is an N in, N out system. N orthogonal input sources get mapped to N orthogonal output beams, using, of order, N phase masks. Although sometimes the number of phase masks can be substantially less, depending on the transformation required. Then the fourth scenario I'll be looking at is temporal shaping. So instead of shaping the beam along the transverse XY direction, how do we shape the beam along the longitudinal direction, the temporal or the propagation axis? This is also a one in, one out system with similarities to the one in, one out spatial beam shaping system, except you apply the phase mask to temporal frequency components instead of spatial frequency components through the use of a dispersive element like a grating. And then finally, we'll look at full spatiotemporal beam shaping, where you take a beam in and you shape it arbitrarily in any direction, be it spatial or temporal. Also a one in, one out system, but the beam shaping is fully 3D now, two transverse spatial axes as well as along the time axis. The only existing system for this kind of beam manipulation is currently a type of one phase mask system, although there's actually more than 10 phase masks in that system overall, but in essence it's a one phase mask system, but I'll get into that later. Okay, so to start out, let's look at what's arguably the simplest possible scenario: coupling between single mode fibers. There's no mode conversion involved per se. We've already got identical Gaussian modes on either side, and we just need to line them up with one another in position and in angle using these two lenses. No phase masks or anything required. But nevertheless, most of the concepts you need to think about when you think about mode conversion are present in this simple example. So here we're looking at what I'll call the forward propagating mode, labeled F, traveling left to right. And then we've got the output beam we're trying to couple into the backwards propagating mode. I've labeled them forward and backward propagating modes in inverted commas because it doesn't actually matter which way the beam is actually traveling. It's the same in both directions, whether you're trying to couple from left to right or right to left. It's all reversible. We're looking at the ideal coupling scenario here, where both the forward and backward modes are identical. If we look at the overlap between the forward and backward propagating modes, everything lines up. What we're looking at here is the forward field multiplied by the conjugate of the backwards field, and if you sum that up and absolute square it in any plane, you get the total power transfer between the two modes. Both forward and backward modes are aligned to one another in this case, so every part of both of the beams are the same. They exist in the same points in space, and they travel at the same angles. They're the same beam. If you summed up the spatially overlapped field between them at any plane along this path, you'd get the full 100% of the beam power of the forward and backward modes. What happens now if the system is misaligned? Here we've got the forward field on the top, the backward field in the middle, and then the overlap between them on the bottom. Let's say the spot coming from the source, F, on the left here, is in the wrong place. It's offset in position at the focus of the lens. Well, when we're misaligned, the coupling between the two modes will be degraded. If we look at the overlap fields at the bottom, we can see that at the focus of both lenses, the overlapped fields has no amplitude. It goes dark. That is, the modes aren't even in the same place, so they're definitely not going to have any coupling between them. If we look in the collimated plane, exactly between the two lenses, the two modes exist at the same place, they're intersecting one another, but they're propagating at different angles. They're misaligned in position at the focal planes, and they're misaligned in angle in the collimated plane. The amplitude of the overlap between the two modes in the collimated plane is maximum. Both modes do occupy the same space. But when those two beams are completely misaligned, if you sum up the overlapped field in any plane, it'll be zero. They're still orthogonal. If you look at the overlapped fields at the focus, it's obvious by eye that it sums up to zero because there's no amplitude. The sum of zero is going to be zero. But it's also zero in the collimated plane due to the phase. So if you sum up that field, everything cancels and the overlap is still zero. It's zero everywhere along the path. It doesn't matter what plane you choose to calculate the coupling, the overlap between them, it's the same everywhere. Here we're looking at a different type of misalignment. This time the input spot hasn't moved, but the input lens is misaligned. The forward beam isn't traveling through the center of the lens, so it's misaligned with the backward beam in angle in the collimated plane, but the two lenses aren't centered on the same optic axis, so the forward and backward beams also don't occupy the same space either. So it's misaligned in both angle and position, but again, the sum of the overlap fields is the same in all planes. In this example, the input spot and lenses are moving together. So in this case, both the forward and backward modes are propagating in the same direction. The beam centers are just misaligned. So in the collimated plane, you can see the position of the forward beam doesn't line up with the optic axis of the backward beam. Phases all line up between the two modes, they're just not in the same place. They occupy different space. Backward field is always centered on the optic axis in the collimated plane, but you can see the forward mode is wobbling either side of it. Again, coupling between the two modes doesn't depend on the plane. The sum of those overlaps is the same no matter what plane you choose to calculate it in. It's a property the modes have as a whole. It has the same value everywhere. Alright, so I keep harping on about the fact that the total overlap between the fields is conserved through propagation. Let's look a little bit deeper at that now. It's a consequence of the fact that a lossless linear transformation conserves energy and it conserves overlaps. If you're moving from one plane to another without any loss or gain in between, like we do here, we've only got free space and phase manipulation, so no light is lost or gained, then we'll also be preserving the overlaps between fields in one plane and the fields in the next. Mathematically, a unitary transform preserves the inner product, the overlap. Meaning if two things were orthogonal before the unitary transformation, they're still orthogonal after the unitary transformation. If they had some overlap before, they've got the same overlap after. If they were the same field before with perfect overlap, then they're the same field after. Probably the simplest way to illustrate that is with the example of a rotation transformation, which is a type of unitary transformation. We've got three orthogonal vectors. You can pretend they're our modes. You can rotate them however you like, but those vectors are always orthogonal to one another. Same thing holds for complex vectors and for other types of unitary transformations. That same rule doesn't hold for other types of transformations, such as scaling along some arbitrary direction. In that case, those vectors aren't orthogonal anymore. So if we apply something like this, which is like loss or gain along a certain direction, they won't be orthogonal anymore. Okay, that's the mathematical description, but if we think about it in terms of optics, why must orthogonality be conserved? Well, I think it's easiest to understand if you think about the contradictions that would arise if that wasn't the case. So let's say we've got some sort of magic, mysterious optical system here, which does the following transformation. It takes in mode 1 on the left, and it maps it to the output mode on the right. And then we've got another input mode, mode 2, which is orthogonal to mode 1 on the left. It's at a completely different position. But then somehow, it also exits the box as the same field as mode 1 on the other side. They both went into the box as orthogonal independent, potentially mutually incoherent fields with no well-defined phase relationship relative to one another. But then they both exit the box as the same coherent field on the right. Now looking at animation like this, you might think that looks fine. That just looks like a beam splitter or combiner. Indeed it does, but if mode 1 and mode 2 have a fixed phase relationship, they're not really two separate modes. They're really just part of the same field. You can just describe them as one mode. Now let's imagine we send both those modes through the device, but there's any and all possible phase relationships between those two modes. So like they're coming from two mutually incoherent sources. And now it starts to look strange, because no matter what the phase shift is between mode 1 and mode 2, we always get the same output. Somehow mode 1 and mode 2 aren't obeying superposition. They're always adding constructively, regardless of the phase shift between them. We put in mode 1, and it transforms into the output beam, interfering only with itself along the way. We put in mode 2, does exactly the same thing, transforms into the output mode, interfering only with itself along the way. Then both together somehow has them always adding up constructively, regardless of the phase shift. Or you can think about it in reverse. We start with the output port on the right, trace it back, but then, the beam doesn't know what phase relationship between the two output ports it's supposed to have. And again, it makes perfect sense if this is just a normal beam splitter, but in that situation, there would be a one in, one out system. There's one mode in and there's one mode out. It doesn't make sense unless you introduce loss or gain. If there's loss, there's no problem. Like if mode 1 doesn't even survive the box, then it makes sense. Or you could amplify a spatial component common to both mode 1 and mode 2 inside the box. That would also work. But it doesn't work if it's lossless. Not if you know that all of mode 1 and all of mode 2, no more or no less, end up at the output. Like the scaling of the 3D axes example from before. So this is a bit of a digression here, but I think this point about conservation of orthogonality is an important point to ram home because it's often not appreciated depending on what your background is. And it's a very important concept when we're thinking about linear transformations of optical fields. Alright, back to the single mode coupling example. But looking at the more interesting case, when the forward and backward beams are spatially different. In the previous example, both input and output were Gaussians. So all we had to do was align the inputs, outputs, and lenses up, and you're done. 100% perfect coupling. If the forward and backward modes are the same size, the focal length of the lenses would be the same. If they're not, you'll have to resize, but perfect matching is still achievable. But what if the modes have different spatial field distributions? For example, let's say we've got a Gaussian beam coming from your source on the left, and you want to couple it into a specific higher order spatial mode of an output multimode fiber, let's say. Our forward beam is a Gaussian beam. Our backward beam is now a Hermite-Gaussian 1 mode in this 1D mode example, a mode with two lobes that are out of phase. The overlap between the two modes looks like this. There's two out-of-phase lobes in purple and green there that will cancel each other when you sum in any plane. The total coupling between the modes is 0, as you would expect because they're orthogonal modes. We can use a phase mask to approximate a transformation between these modes by attempting to correct the phase differences between those two modes. If we imagine our Gaussian and our HG1 mode meeting at the waist of the collimated plane, where we'd like to put our phase mask, that discrepancy between the forward and backward modes is what we need to at least approximately match using the phase mask. So, we apply a phase mask, which has the phase difference between the two modes in that plane, in an attempt to match them. The flat-phased Gaussian, traveling left to right, gets a pi phase flip imposed on it, which gives it two out-of-phase lobes, similar, but not exactly the same, as a HG1 mode. The HG mode, traveling right to left, already consists of two out-of-phase lobes, so when it propagates through the phase mask, it becomes two in-phase lobes, similar but not exactly the same as a Gaussian. And similar but not exactly the same is the operative word here. We can match the phases between the modes using the phase mask, but we can't fix the difference between the amplitude distributions of those two modes. The Gaussian has a peak at the center, the HG mode has a null at the center, and the phase mask can't fix that. It can't put amplitude where there is no amplitude, it can only align the phases. As a consequence, some loss will be incurred. It's not a lossless transformation between the two modes, it's only approximate. If we look at it in 2D for a second, here we have our spatial light modulator, which is how we'll implement a phase mask, let's say. Let's say we've got a Gaussian as our forward mode, and an azimuthal index equals 19, Laguerre-Gaussian mode as our backwards mode. Those modes are very spatially different. The Gaussian occupies almost completely different space to the large L equals 19 mode. The whole Gaussian fits inside the null of the L equals 19 mode effectively. Now sure, you can match the phases, but there's still going to be a lot of loss because of that amplitude mismatch. Your phase mask can't really match the phase if the modes aren't even in the same place. You could resize the modes using a different magnification on your lenses, and that would help. It could potentially help quite a lot because the modes are now much more similar in size. But ultimately, there is still an amplitude mismatch. The configuration we've been looking at here, where you use a phase mask which encodes the phase difference between the modes being coupled, gives you the maximum power transfer between the modes. If you're coupling into a fiber, let's say, this simple phase matching approach will allow you to couple the maximum amount of power into your target mode. But where does the rest of the power go? The power that you couldn't convert to the desired mode. It's distributed amongst other spatial modes, some of which might be supported by the fiber and will degrade the purity of your mode excitation in the fiber, and some of the modes won't be supported by the fiber, and they'll become loss. What we're looking at here is the field in the image plane. So that is the plane of the phase mask. It's got a Gaussian amplitude with a simple helical phase imposed on it by the phase mask. Then below that, we've got the Fourier plane of the mask, which gives us something that resembles the desired LG mode. And then we've got the graph on the right, which tells us how efficiently each of the first 55 LG modes are excited by that mask. So points on the graph are illustrated as the modes themselves to make it easy to interpret by eye. Ideally, you'd have 0 dB loss for the desired mode, so no loss, and infinite loss for all the other modes, meaning you've excited the desired mode completely and no other modes. It's possible to calculate more complicated masks using computational holography algorithms like Gertzberg-Saxton, for instance, but there are many algorithms out there where you can trade off a bit of extra coupling loss in the mode of interest for a lot of suppression in those other modes you don't want, after spatial filtering the Fourier plane by coupling into a fiber or passing through a pinhole. By redistributing the amplitude differently in the Fourier plane, by shaping the phase in the phase mask plane, you can work around the fact that the amplitude distributions of the two modes you're trying to convert between are different, and hence you will have to incur loss, but you can at least decide how you want that loss to be spatially distributed in the Fourier plane. You know you're going to have some loss, but at least you get to choose where that missing power ends up, hopefully not in any spatial modes or areas of the Fourier plane you actually care about. Just dump that power somewhere out of the way. A common approach is you set up an area of interest where the fiber core is, and then you run the algorithm. You can think of it as like pumping the amplitude noise out of that central core region and dumping it into the background area where it won't be coupled into the fiber at least. Or perhaps you're passing it through a pinhole filter. It's possible to avoid the inherent loss of a single phase mask approach by using two or more phase masks separated by a Fourier transform or just sufficient free space propagation distance. For the two-plane approach animated here, we've got the same scenario as we saw earlier, with a Gaussian mode coming from the left and a HG mode coming from the right. Those two modes differ both in their amplitude distribution but also their phase distribution, and that difference in amplitude distribution was what limited the efficiency at which you could transform between the two using a single phase mask from before. When you've got two phase masks, you can think of it a bit like the first mask redistributes the amplitude onto the second mask, and then that second mask finishes it off by just matching the phase, much like the single mask approach from before. Looking here, we've got the Gaussian spot comes in, gets collimated, hits the first phase mask, which imposes a phase front onto the beam, which causes the single lobe of the Gaussian to diffract into two lobes of the HG1 mode, incident on the second mask. That second mask then fixes whatever phase differences remain between the beam and the desired HG1 mode, and then you're done. So this simulation is not strictly 100% efficient, but it's like 99%. If you imagine these phase masks are implemented on an SLM that's reconfigurable, it also allows you to excite many different sized modes using the same system, because the two-phase mask approach allows you to resize the beams. Unlike the single-phase mask approach, where you're reliant on the amplitude distribution of the two modes being converted to be hitting at least approximately the same regions of the phase mask. When you've got two phase masks, you can control where the amplitude hits the second mask, so you can compensate for mismatches like that. You're not so reliant on the fixed lenses for the resizing, you can also do some resizing using the phase masks. The idea of using planes of phase manipulation to transform modes can be extended from that one in, one out case we've been looking at so far, to the more general case of n modes in and n modes out. In this scenario, instead of just a single field coming in, that we want to transform to a single field going out, we need to develop a system that can independently transform n input fields and then map them onto n output fields. In the animation here, we've got three spatially separated beams coming in on the left, and then each one of those beams gets transformed into its own HG mode on the right. And remember, if the input modes are orthogonal on the input side, they'll have to be orthogonal on the output side as well if we're lossless. In general, you can't do that type of transformation with a single phase mask. And let's have a look at why not. Why can't we just do a matrix-like transformation like this using only a single phase mask? Let's say our orthogonal mode 1 coming in is a tilted Gaussian beam. It looks like a spot at the input, and once collimated on the SLM, it looks like this big tilted Gaussian. And we want to transform that into an on-axis Gaussian at the output. Pretty straightforward. Now for mode 2. it comes in as a Gaussian beam at a different position, which in turn becomes a Gaussian beam tilted at a different angle on the SLM. And then we want to transform that into an on-axis LG mode. Two orthogonal spots come in, two orthogonal modes come out. No problem from conservation of energy or conservation of orthogonality point of view, but the real problem is that both modes occupy exactly the same space on the SLM, on the phase mask. Whatever phase mask you apply to mode 1, it applies exactly the same to mode 2. They're not independently controllable. So if you make a phase mask for mode 1, unless it just so happens to also be exactly what you need for mode 2, it's not going to work. Again, they're not independently controllable knobs that you have access to. So something like this would be fine, because both spots just need to be tilted by the same amount, so there's no problem. One mask satisfies both of them. This Fourier mode on the phase mask plane example is a bit extreme in that all the modes have exactly the same amplitude profile on the phase mask. But it's essentially the same problem with other mode bases as well, when you're working with just a single phase mask. The other extreme would be two completely separated spots on the phase mask. Now you can apply completely independent phase masks to each spot, but you're not going to be able to get them to propagate in the same direction in the Fourier plane. There's still constraints on the types of transformations you can do. In order to do an arbitrary transformation, you need to be able to control both the position and angle, i.e. you need to be able to control both the amplitude and phase distribution of the fields, and also the positions of where those fields are relative to the other fields. And you can't pull that off arbitrarily with a single phase mask. With a single phase mask, you've got those constraints in terms of what's possible. But if we add many phase planes, then we'll gain the ability to perform arbitrary mappings. The amplitude distributions of each input mode can be redistributed through the transformation, such that you can start to apply the transformations you desire between orthogonal fields. Now we've got what's called a multiplane light conversion system, MPLC, a system that performs an arbitrary spatial transformation between n modes on one side and n modes on the other side. In this animation, it's a transformation between a 1D array of 45 Gaussian spots and the first 45 Hermite Gaussian modes, but it could be any transformation between two different spatial bases, two different sets of orthogonal spatial fields at the input and the output. An MPLC has similarities with multi-port interferometers based on Mach-Zehnder interferometer meshes, because these also implement arbitrary unitary transformations between a set of inputs and outputs, typically implemented using single-mode waveguides. So this multi-port interferometer here, it also uses cascades of phase shifts across multiple layers, whereby tuning two phase shifters inside those Mach-Zehnder blocks, you can redistribute the amplitude and the phase of the light in the waveguides presented to the next stage. And in such an implementation, light is distributed from one plane to the next using waveguides. In MPLC, we have phase shifts implemented on discrete phase masks, and the light is distributed to the next plane through diffraction. And MPLC has the advantage that it can manipulate the beams in 2 dimensions rather than just one. It's a volumetric device rather than a flat device. And similar to a multi-port interferometer approach, if you want to implement a transformation between a set of n modes on one side and n modes on the other, in general, you'll need of order n planes of phase manipulation. And then, if you want to make the transformation more broadband, make it work over a wider operational bandwidth, then you'll have to add yet more phase masks. And then in the extreme case, you can imagine if you had an infinite number of phase planes, all infinitely closely spaced, then you'd have a very smooth 3-dimensional refractive index profile that would naturally have a very high bandwidth, an adiabatic transition between a set of input modes and a set of output modes, with only very subtle phase changes in each of those many planes. To design an MPLC system, we use a wavefront matching approach, which works like this. The idea here is we've got n modes coming in from the left, and we've got n modes coming in from the right, and we want to make a lossless transformation between these two sets of modes, using the phase planes in between. Now remember, in order for it to be a lossless transformation, we need the fields coming from the left and the fields coming from the right to be the same everywhere in space. We need that overlap between the forward and backward modes to be 100%. They're exactly the same. The coupling between the two is 100% perfect. And we're going to attempt to achieve that using the phase planes. Whatever the phase discrepancy is between the forward and backward modes, we're going to try to fix that with the phase masks. So what you do is you propagate all the modes in both directions to the first plane. So they're meeting here at the first plane. And then at that plane, you get the spatial overlap between each pair of input and output modes that you're trying to match. And then you sum all those spatial overlaps together, and then you take the phase of that and make it your phase mask. So that is, you make the phase mask the average phase error of the forward modes versus the backward modes. You make a phase mask which on average tends to maximize the coupling between the forward and backward modes. And then you propagate to the next plane. And then you do the same thing. You overlap each pair of input and output modes, sum those spatially overlapped fields together, and the phase of that sum becomes your new phase mask. And then you keep going like that, plane to plane, forward and backward, matching phases, and as you do that, those forward and backward modes will tend to converge, as best they can at least, to maximize the coupling between the input and output. It's a process that's a bit like a Gertzberg-Saxton type algorithm, and then it doesn't have an error function that's directly calculated, and then decisions are made about the next solution to try based on that error metric. Rather, it's a process of continually propagating from plane to plane, and through feedback and reinforcement, continually, spatially filtering the solution closer and closer to the desired result. You keep matching those phases, trying to reinforce the transformation that you want, and nudging it closer and closer to the solution by maximizing that coupling. So like a GS type algorithm, it converges pretty quickly towards a solution. Now there's also a lot of tweaking and playing around in order to get the best possible solution. The solution space is pretty enormous, and there's certainly no guarantee that you'll get the optimal solution. But that's the basic premise. As I mentioned, if we've got n modes being transformed, in general, we'll need of order n phase planes. However, there are some special case transformations that don't require that full of order n phase planes. Some transformations can get by using much, much less. Classic example. Let's say we want to do a spatial Fourier transform. Well, then we don't even need any phase planes really, because free space will naturally do the Fourier transform, or so will a lens. And that's just one plane of phase manipulation. Doesn't matter how many modes there are, it's always just the same number of planes. And there are other special cases where many modes can be transformed using relatively few planes. It turns out there's another special case of practical relevance, which was only discovered relatively recently, and that's the Hermite-Gaussian mode sorter. If you set up your transformation such that you map a Cartesian grid of spots to the Cartesian indices of the Hermite-Gaussian modes, then you can transform many modes using relatively few planes. And once you're in the Hermite-Gaussian basis, you can transform into the Laguerre-Gaussian basis using two cylindrical lenses. With that approach, examples of 210 and 325 modes were demonstrated using just 7 planes, implemented on a single SLM. So the number of plane scale is more like the square root of n now rather than n. But importantly, it has to be Cartesian spot position maps to Cartesian indices of the Hermite-Gaussian modes. You can't just randomly assign spots to Hermite-Gaussian modes, otherwise the number of phase planes you need will blow out to something that's more like the traditional n planes for n modes. It has to be that specific mapping which allows the transformation to be done using a heavily reduced number of planes. It's a neat device because it's relatively simple in terms of its experimental implementation. It's just a SLM which contains the 7 phase masks and a flat mirror. In the supplementary material for this paper, there's example phase masks pre-calculated for many common SLM types. So if you were interested, you can just download that and use them as is. But there's also provided MATLAB code for calculating your own masks, changing the mode basis, changing wavelengths, etc. So there's a bunch of tools for that available online if you're interested. These are example fields you get on the Laguerre-Gaussian mode side of the device as we feed light into each one of the spots on the spot array side. The device is of practical interest for a few reasons, one of which is it allows you to multiplex and demultiplex HG or LG modes into a common beam for applications in classical or quantum communication through free space or optical fiber. So it's useful as a type of mode multiplexer, but you can also think of it as a new type of optical element which gives you access to a new type of spatial transformation for analysis or filtering. By analogy, it's common to use a lens to perform a spatial Fourier transform, use the lens to decompose the beam into its spatial Fourier components, and then in the Fourier plane you filter off certain components or analyze certain components. Some features or aspects of a beam or image are more easily identifiable in the Fourier domain, but not really identifiable in the real space, and vice versa. Well, the LG mode sorter gives you access to the Laguerre-Gaussian transformation. So whereas a traditional lens decomposes a beam in terms of linear momentum, so that is k-space, the Laguerre-Gaussian mode sorter decomposes a beam in terms of orbital angular momentum. In the LG domain, features such as circular symmetry are localized, and you can use that to filter out components of your beam that are circularly symmetric, for example. It's another type of spatial transformation you can use for optical signal processing of various forms. A special implementation of the Laguerre-Gaussian or Hermite-Gaussian mode sorter is to arrange the spot array not in a 2D Cartesian grid, but to add extra phase planes to rearrange that 2D spot array into a 1D line. In this example, we've got a 2D beam coming in from the right, which maps onto a 1D array on the other side. So it's a bit like taking a 2D image and then rearranging the image such that all the pixels are in a single line. It's got all the same information in it, but you've sliced and stacked it up into a single dimension. That can be useful for interfacing with things like waveguide arrays or photonic integrated circuits, but it's also useful for analyzing or manipulating 3D beams using 2D surfaces, and I'll discuss that in a bit. This is what one of those 2D to 1D transformations look like in practice. You've got a 1D V-groove fiber array on one side. You've got a lithographically etched set of 14 phase masks. You've got a mirror. And then off into free space, you've got the 2D mode side. All this discussion so far, we've been talking about spatial transformations, whereby we take a single beam or multiple beams in, and then transform them spatially onto a beam or beams at the output. So this is transverse shaping of the beam, shaping the beam in what you'd normally define as the x and the y axis. But what about shaping the beam along the longitudinal axis, along the time axis, along the propagation axis? Let's forget about spatial shaping for a moment and just look at temporal shaping. One way you can do that is with an optical modulator, some sort of perhaps electro-optical or acousto-optical device, whereby let's say you feed in an electrical signal and then that signal gets imposed on the amplitude and or phase of the beam you're modulating as a function of time. So you're manipulating the beam directly in the time domain by changing the properties of the optical system as a function of time. If the modulation you're trying to impose on the beam has a bandwidth that's compatible with electrical signals, so gigahertz, then that's a good way to go about it. But what if the bandwidth of the modulation you're trying to impose on the beam is higher than that, say terahertz? Maybe you're working with a femtosecond laser and you want to manipulate the beam on that femtosecond timescale. Well, in that case, you typically use a frequency domain technique like spectral pulse shaping. It's a technique that's been around since the 80s. The idea is you split up the beam into its spectral components, manipulate the amplitude and or phase of those spectral components, and then when you put those spectral components back together, you'll have some corresponding modulation in the time domain. The advantage here is that the system can manipulate the beam on femtosecond timescales without the system having to have the ability to change on those femtosecond timescales. It's a quasi-static device. How does it work? The idea is you take the pulse in and then you decompose it into its spectral components using a dispersive element like a grating or prism, etc. That dispersive element maps the wavelengths to angles. So that is, it maps the temporal frequency to a spatial frequency. In the Fourier plane of that dispersive element, you've now got access to the individual frequency components, those spectral components which made up your original beam as separated spatial positions on your mask. Then you can apply a phase mask to those spectral components to independently manipulate the amplitude and or phase of those frequency components, such that when you put them back together again, you've manipulated the temporal behavior. I know when I first learned about spectral pulse shapers, I didn't really have trouble understanding how they work in a mathematical sense. You manipulate the frequency domain properties and you get a corresponding time domain manifestation of that. Fair enough, I believe you. But the next question is, okay, but physically, where does the light go? How is it being delayed? It's not magically slowing down mid-air. That light has to be going somewhere, and if it's showing up early or late, it has to have taken a longer or shorter path somehow. And indeed it does. If we look at light returning from the phase mask back onto the grating, delay is a linear phase ramp versus frequency. So if we apply a linear phase ramp on our phase mask and trace it back through the grating, we see that the light takes a longer or shorter path back through the grating, depending on where you steer the light in. The maximum amount of delay you can produce, assuming your grating is big enough, relates to how steeply you can steer that beam along the frequency/time axis, which is a function of how fine the spectral resolution is at the plane of the mask. You want very fine spectral slices and also very high resolution on your mask as well, so you can address them, because you want to apply as much phase as possible per unit frequency in order to create large delays. You need that dispersive element there, like the grating in this case. This wouldn't work with a mirror because the light bends the wrong way and the delays equalize instead of add. If it was just a mirror there, you hit one side of the mirror, you enter the mirror early, but you leave it late after the reflection, or you take a longer path to the mirror, but a shorter path away from the mirror, such that it all cancels out and there's no net delay introduced. Whereas in the spectral pulse shaper, if you take a long path in, you also take a long path out, you take a short path in, you also take a short path out, so the delays add rather than cancel. For our final system here, we're going to look at a combination of both spatial and temporal shaping in the same beam. Spatially and temporally shaping an optical field arbitrarily. So that is sculpting the beam fully in 3 dimensions to create little volumetric blobs of light that fly through space. So shaping the beam in the spatial transverse direction, as well as the temporal longitudinal direction. Completely arbitrary spatiotemporal beam shaping, where you can control the amplitude and the phase and the polarization state of every point in space at every point in time. We looked at this within the context of creating optical time-reversed waves. So in a normal scattering process, for example, light comes in, it propagates through some complex media where it becomes scattered spatially and temporally. Now we want to flip the time axis of that blob of light and send it backwards through the medium, and in doing so, recreate that original field. The idea there is that the ability to create time-reversed waves lets you deliver light through objects in ways which would traditionally be prohibited by scattering. You couple in the pre-scattered field, which then becomes the desired output field through the scattering process itself. However, the tricky bit is that that spatiotemporal scattering process through the complex medium is completely arbitrary. That volumetric light blob the complex media outputs is just random looking. If you want to create that light blob, you need to be able to completely control the amplitude, phase, and polarization at every point in space and time inside that volume there without any constraints really. The blob could be anything, and hence you have to be able to make anything. But experimentally, how do we generate a 3D beam using 2D phase masks? So far, we've been looking at either generating 2D spatial patterns or 1D temporal beams, but now we're talking about something that's truly 3-dimensional in nature. But experimentally, we only really have optical components like spatial light modulators, which are flat 2-dimensional devices. How are we going to pack that 3D information about our light blob onto the 2D surface? Well, we can use that 1D to 2D spatial transformation from before. That'll take a 2D beam and map it onto a 1D line and vice versa, freeing up an extra dimension to use for temporal shaping. So through the optics of the system, the SLM will be carved up like so, allowing the 2 spatial dimensions, one temporal/spectral dimension, as well as the polarization dimension, to all be controlled using that single phase mask on a flat 2D surface. Let's have a look at how such a device works. First, I'll simplify that diagram a bit and get rid of some of the polarization optics, mirrors, other stuff that you do need in practice but isn't really that important conceptually. Light comes in from the source. It passes through 3 cylindrical lenses, which collimate the beam along the time axis and image the beam along the space axis. Passes through the grism, that's our dispersive element. Then it passes through a few cylindrical lenses that perform some resizing and put us in the Fourier plane of the grism, where the spatial light modulator is. The SLM has access to fine spectral slices along the spectral axis. That'll allow us to access long delays. And it has a wide beam, top to bottom, along the spatial axis, which will allow us to access many spatial modes, and we'll get to that in a moment. The other polarization component is basically the same, it's just on the other side of the SLM. The beam reflects off the SLM, passes back through the lenses. Now we're at the grism. We're in the Fourier plane of the SLM. If we steer light up-down on the grating using the SLM, we'll be addressing different spatial modes. I'll talk more about that in a second. We can effectively choose different 2D modes from a 1D list selected along this axis. And if we steer light left-right on the grating, we'll be addressing delay, just like we did before for the traditional spectral pulse shaper. And if we create complicated distributions of field in both the up-down and left-right directions, we'll be creating complicated spatiotemporal combinations. Looking at the top of the grism, we can see that as we steer the light along the spectral axis on the SLM, it's creating delay in the path back through the grism. Back down to the table. At the grism, we've got this funny looking blob of light, whereby one axis represents the spatial properties of the beam we want to generate, and then the other axis represents the temporal properties of the beam that we want to generate. And this should hopefully make a bit more sense in a moment. As we propagate back through those input cylindrical lenses, we end up with this 2-dimensional light sheet, where one axis represents the spatial beam shapes, that's the space axis of the beam, that tells us what combinations of 2D spatial modes we want to generate, and then the other axis represents time, that tells us at what delays we want to generate those 2D spatial mode combinations. You can think of that 2D light sheet like sheet music or a play a piano roll. But instead of the sheet music telling you what note combinations to play at what times, our light sheet encodes what 2D Laguerre-Gaussian mode combinations to play at what times. We pass that light sheet through our MPLC 1D to 2D spatial transformation, which converts our 2D sheet into a fully 3D beam, where we can specify the amplitude, phase, and polarization of every point in space and in time, full arbitrary vector spatiotemporal beams. You can think of it as like an ultra-fast wavefront shaper, which has a frame rate of 4.4 terahertz. It has the ability to generate about 90 completely independent spatial and polarization wavefronts, each separated by about 230 femtoseconds. And it really all hinges on that 1D to 2D transformation, which lets us map the 3D beam onto a 2D surface. The MPLC 1D to 2D transform acts like a 1D lookup table, which lets us select from a list of the first 45 Laguerre-Gaussian modes, which are 2D modes. Then as we pass in our spatiotemporal 2D light sheet, the MPLC converts that into a 3D volumetric beam. Here's an experimental example of a radially polarized so-called clock hand beam that's spinning around at a rate of 1 rotation per 5 picoseconds at the far end of a multimode optical fiber, a demonstration that requires full control of space, time, and polarization. And in that work, we also did a bunch of silly beams as well. So this one was a modal Eiffel Tower. So that is, it's a little model Eiffel Tower shaped beam flying through space at the speed of light. Okay, that's it. Thanks for listening. We looked at a bunch of different scenarios, both in the spatial domain and the temporal domain. We looked at one beam in, one beam out, single phase mask. We looked at one beam in, one beam out, multiple phase masks. We looked at multiple beams in, multiple beams out, multiple phase masks. We looked at temporal shaping. And then finally, we looked at a bit of combination of a few of those concepts in one in terms of an arbitrary spatiotemporal beam shaper, which shapes the beam both spatially in the XY direction and also temporally in the Z or time dimension.